Last time, we were looking at M22 matrices that are 2 by 2, and we had you come up with a basis other than the standard basis. I happen to pick this one because he's nice and easy to remember, and we'll go ahead and transfer that to the top of the next page. Now, I want you to take and write these guys and make a linear combination of these guys to create this vector 3, -1, 0, 2. So C1 plus C2 plus C3 plus C4 should equal the vector, which is a matrix, 3, -1, 0, 2. Okay. So I'll give you a second to do yours, and I will compute mine as well. Okay, so I caught a tiny mistake I made. So the fourth matrix should have been 1, 2, 3, 4. I caught that, and then we put him into the linear system, solve him, and find out that 7/2 of this minus 1/2 of that minus 1/2 of that plus 1/2 of this gives us, in fact, the desired guy. In fact, you can pick any one of the components just to double check. 0 minus 0 minus 3/2 plus 3/2 is, in fact, 0 in the 2, 1 position. Okay. And you'll notice that no matter what your basis is, each of you will have 4 vectors in your basis for M22. Okay. So what I want you to do now is think about finding the dimension for each of the following common vector spaces. So we'll give you a second to pause the video, find the dimension of Rn, P sub n, M sub n, M by n, and C negative infinity to infinity, the set of all continuous functions on the entire real line. Hopefully you got n, n plus 1, m times n, and this one is a little tricky, but he's infinite dimensional. Now, the most common mistake here is that this guy is, and some people say that the dimension of P sub n is n plus 1, but if we think about this, if we're trying to do polynomials of degree at most 2, we've got the x squared component, we've got the x component, and we've got the x to the 0th component. So even though it's x squared, we need not 2, but 3 pieces for his dimension. And why do we want to know the dimension? Well, it can help us in analyzing our vector space. So if we know the dimension of the vector space and we have a set of vectors, and if there are more vectors than the dimension of the vector space, then what do you think? Pause, wait for it. You're right. If there's more vectors than the dimension of the space, then the set of vectors are linearly dependent. Okay. If, on the other hand, we have fewer than n vectors in an n-dimensional space, did you get that? The vectors will not span. Okay. There's just not enough vectors to cover the entire space. And finally, if a set of vectors S has exactly n vectors, it will be a basis if either it spans or is linearly independent. So this is a great sale. So if we know the dimension and we have the appropriate number of vectors, that same number of vectors, we will know it's a basis if it either spans or is linearly independent. So we only have to check one to the other, we get the other one for free. So if we have 4 vectors in a 4-dimensional space, if I can show that they are linearly independent, then it's guaranteed to span. Or conversely, if I can show that the 4 vectors span, then they must be linearly independent in that 4-dimensional space. So just a few things just to wrap up here. on 5.4 basis and dimension. If we have the vector 1, 3, 0 and the vector negative 2, 0, 4, do they form a basis for R3? Explain. The answer is no. There's not enough vectors. There's only 2 vectors in a 3-dimensional space. So what could we do to form a basis? We could add one more vector, but he has to be special. That vector has to be linearly independent on the other 2. Okay, I can't just add the vector 2, 6, 0 because that would be linearly dependent on this guy and wouldn't increase my reach any, increase my span. Okay, what about this guy? 1, 1, 2, 3, and negative 1, 2, do they form a basis? No. So why? There were too many vectors. Therefore, they were linearly dependent. So what could we do to turn this set of vectors into a basis? Well, as we saw back in our previous section, you can take and express one of those vectors as a linear combination of the other vectors. And if you can do that, then that one vector you can throw out as unnecessary. So for example, I could show that negative 1, 2 is a linear combination of 1, 1 and 2, 3. So I could cut out the linearly dependent vectors until I get down to a basis. Okay. All right. So based on these right here, I want you to put the plus minus theorem in your own words. In essence, if we have a set of vectors that spans but is not a basis, since he spans, that means he's got enough vectors, and if he's not a basis, then he's got unnecessary vectors. So we minus or take away vectors that are linearly dependent until we work our way down to a basis. If we have a set of vectors like here that are linearly independent but are not a basis, we can plus or add vectors to them that are linearly independent to the ones we already have until we reach a basis. And once we have that basis, we are just right. Okay, we'll see you next time.